Hello everybody, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be talking about all of the design rules that you need to start a new HDI project. Now this all came up because of a comment I received over on my YouTube channel, and I thought it would be a really great topic to discuss here on Altium Academy because of course we can hop into Altium Designer and actually see how to implement some of these design rules for a new HDI project. We're going to look at some typical values from an HDI manufacturer here in the US, and we're going to encode some of those values in the design rules inside of Altium Designer, so you're going to be able to see where exactly all of those rules are located. Let's go ahead and hop in and get started. Now this video is all about the design rules that you need for a new HDI project. And whenever you're doing an HDI design, you need to find the manufacturer capabilities. That is always the first place to start when you start figuring out what the design rules need to be for your project. Now I think it's always a good idea to have a manufacturer in mind that you want to use and make sure that you consult with them regarding their capabilities and their documentation requirements before you start designing your PCB. And a lot of manufacturers will put this information on their website. Even if they don't put this documentation on their website, you can always email the company and they should send you a fabrication capabilities statement. If they also do assembly, they should send you information such as kitting requirements, attrition requirements, any sort of ordering or documentation requirements. Make sure that they give you all of that information before you start your PCB project. Now, in order to show how to implement all of this information inside of a PCB doc file in Altium Designer, we're going to use the fabrication capabilities from Advanced PCB. They're an American manufacturing company that does PCB fabrication and PCB assembly. I also have their manufacturing capabilities pulled up on screen. Let's go ahead and take a look. So here I am first inside of Altium Designer, and before we take a look at the manufacturing capabilities from Advanced PCB that you can see I have here on screen, we're just going to briefly look at where to access some of the design rules inside of Altium. The project that we're looking at here is our NRF52 module. You can see that we have a BGA right here. You can see the antenna feed line going out to the microstrip antenna, and then here you can see we basically have via in pad fan out inside the boundary of the BGA. Now, one of the things that's really important in these designs is the pitch between the pins in these components. And you can see here, just with a quick measurement of the pitch on this design, it is 0.35 millimeter pitch between the pins on this BGA. Now that number is really important because it's going to determine how large the vias can be. Of course, we're going to run up against the clearances and we'll get that information from the fabrication capabilities, but we need to know how big can the vias be? Can we route in between the pads? What are we going to do on the inner layers versus the outer layers? How many vias are we going to have stacked on top of each other if we're doing stacked blinded buried vias? Those are all important things that we need to know ahead of time, and we learn all of that from looking at the BGA footprint. Now, as we'll see later in the video, we may also have to decide between the use of solder mask defined pads and non-solder mask defined pads. And that is also related to the via size that's used in a component like this when you're doing via in pad fan out. Now, one really useful feature that you can use to control the design rules in the BGA region versus all the other regions of your PCB layout is the rooms feature inside of Altium. So in order to create a room around a component, you can just select the component, go up here to Design, go to the Rooms submenu, and then click Create Rectangular Room around selected components. And that's going to create a region in the PCB layout where you can basically define specific design rules that apply only inside this room. Now you notice here, sometimes it makes the room a little big. What you can do is, of course, just select it and resize it just like any other object inside of Altium Designer. Here I'm going to make it a little bit smaller so it just gets right up next to the pads. And then that's going to ensure that any design rules that I create that I only want to apply to this part of the layout, I can use the within room query inside the PCB rules and constraints editor to define the rules to apply only to stuff or objects that are in this region of the PCB. Once we create this room, we need to give it a name. Here I'm going to select the room and I'm just going to name it BGA room. So that's my room where all of the BGA specific design rules are going to apply. And as we'll see when we look through the fabrication capabilities, that's usually what we're looking for when we want to start an HDI design. We're going to look for the design rules that we need to apply mostly in this region of the design. Now, what design rules would we want to define specifically in this BGA region versus other parts of the PCB layout? Well, let's take a quick look at the Design Rules and Constraints editor and we can get a good idea. Now, I think one of the most important rules that you want to define just in the BGA regions is the routing via style rule. So here, if I want to create a new rule that only applies to that room, we would just right-click, hit New Rule, and then I open up that new rule and I want to select Custom Query. Then in order to ensure that this new rule only applies to that specific part of the PCB layout, I'm going to use the Within Room query. You can see here that when I select Within Room, it then brings up a drop-down list of all the rooms that are currently in the design. I'm just going to select my BGA room, and there we go. You can see it auto-completes. Then I would enter in the values that I want to use just for the via hole and the via pad inside of that BGA region, and then it's going to automatically enforce those inside the PCB layout after we click OK on this dialog. Now, this is a really useful feature if you have multiple BGAs that have different pitches and you can use different via styles to do the fan-out routing. For example, you might have one of your BGAs be in this very fine pitch 0.35 millimeter package, and it needs to have blind and buried vias in order to do the fan out, but you might also have, for example, a 0.8 millimeter package. Maybe it's a DRAM chip. You could use through holes for that package and complete the fan out that way. You can enforce the different rules in those different regions using the rooms feature inside of Altium. Two other important ones are routing width and electrical clearance. So the routing width is important because you can have different line widths or different minimum line widths on different layers of the PCB. So on outer layers versus inner layers, for example. Same applies to clearances. You can have clearances on different layers, and you may even want to enforce different clearances in different regions of the PCB. So for example, inside your BGA region, where you're doing either dog bone fan out or via in pad fan out, you might want to enforce narrower or thinner traces just for doing the fan out routing, but then once you leave the BGA region, you could fan out those traces and make them wider for the rest of your route. Now, in order to do, let's say, a room-specific and layer-specific clearance rule, for example, we would right-click here on Clearance, hit New Rule, and then we would want to also implement a custom query. So here, in our custom query, we would say Within Room, and select our BGA room. We would then use and then we would say On Layer, or In Layer Class. So in layer class, we could then define a layer class that just has our outer layers once we define our layer stack. And then this clearance would only apply, for example, to outer layers. We could then set up a different room for the inner layers if we want. Now let's take a look at the manufacturing capabilities from Advanced PCB. Please note that me showing these capabilities in a video on the Altium Academy channel does not constitute an official endorsement by myself or Altium. So here I have Advanced PCB's capabilities here on screen. And one thing I'd like to note is that Advanced PCB is one of the few companies that breaks out their capabilities by specific facility. So in this dropdown, you can see here they have multiple production facilities. Just for example, if I click on the Chandler, Arizona option, you can see that the capabilities in this table are different. So for our purposes, we're just going to use the Santa Clara capabilities for simplicity. Now the other thing that they do is they break this out by a standard capability and an advanced capability. And the advanced capability is typically something that you would use for an HDI board or possibly an ultra HDI board where you're pushing those trace widths and clearances down at 2 mil or possibly even less. So here as we look through here, we can see a few important points immediately in the top section of this table, and that is the minimum core and minimum dielectric thickness. Now this is very important for HDI designs because if you're familiar with blind vias, specifically laser drilled blind vias or laser drilled buried vias, the via size that you can use is very closely related to the core or dielectric thickness. So if you're using a dielectric on the outer layers for blind and buried vias and you're doing laser drilling for processing, you want to keep the aspect ratio of those drills less than 1. And they actually have aspect ratio limits that they list elsewhere on this page, and other fabrication houses will do the same. Another important point here in this table is the number of lamination cycles for rigid materials. And here you can see they listed at 5x for their standard capability or 7x for their advanced capability. So this basically tells you how many times you can laminate new buildup layers on top of your central core layer stack in order to build up your HDI stackup. So basically what that means is that for the 7x lamination cycles option under their advanced capability, it means that you could take a central core that's already been laminated once and then laminate that core with more buildup films 6 more times, basically building up 6 dielectric layers on each side of a central core. Next, let's look at trace width and spacing for the standard and advanced capability. So here in the standard and advanced capability, you can see that the trace width and spacing are actually a function of copper weight. And that is really important because in HDI designs and in UHDI designs, we typically are working with 1/2 ounce copper or less. The base copper that you might start with on a design could be as low as 1/8 of an ounce, especially in a UHDI design. And then on the outer surface layer, that's going to get plated up maybe to 1/4 ounce. Now what they're specifying here is the base copper thickness. So basically the unetched, unplated copper. This is going to be the trace width and spacing that you're going to be allowed to use in this design. Now, these numbers here are global numbers for the inner layer and global numbers for the inner layer spacing. You see that we also have numbers here for the outer layer spacing and the outer layer trace width. So what this means is that you could select these numbers and apply them as a global value in your design rules. You don't have to make these numbers specific to the BGA region. You can if you want to, but you don't have to. Now let's go ahead and take a look at the next section, which is our etch requirements. And one of the most important entries from this section is the minimum copper sliver between antipads. So what this number basically says is that if I have a differential pair and I route it through vias and I put those vias through a plane, the plane is going to have some antipads that allow the signal vias to pass through. And in order to maintain a continuous plane in between those two vias, there has to be some minimum amount of copper between those antipads. Now inside of Altium Designer, this would refer to this small section of copper right here that we see for these two vias. Now these two vias aren't part of a differential pair, but the same constraint still applies. If I want to maintain continuous ground between these two vias, I'm only allowed to do that if there is some minimum amount of copper in between the two vias as defined by this antipad. And we can see that here even on the internal layers. So right here on layer 5, you can see here that we're maintaining some copper sliver in between these two via pads. Now, since we're talking about vias, this is a good segue into the next section, which deals with drilling and routing. So as you can see here, we have all of the information that we need for drilling, both with mechanical drills and with laser drills. So as we scroll down here, you can see that we have a section on laser drills. Now, one of the things that is important in this list is the minimum laser drilled pad size and the minimum pad size. And then you can see here we have some information on aspect ratio requirements for laser drilled blind vias. Same thing here, we have minimum drill size and maximum drill size, and you can see that for their advanced capability, the minimum drill size gets down to 3 mil. So based on this information, you would want to choose a via size that's going to align with the capability that also allows you to complete your via in pad fan out for a fine pitch device or dog bone fan out for a more coarse pitch device. Now here, this aspect ratio number is important because that's going to tell you the maximum layer thickness that you can use once you decide on the drill diameter and the pad size. So in our example in Altium, let's say that we're going to use their advanced capability. If we have their advanced capability and I select one of the vias here in the BGA region, just go back up to the top layer, we can then determine what the layer thickness would need to be in order to accommodate that. So up here on the top layer, if I just select, for example, this via, you can see here that the hole size is 4 mil. So based on a 0.8 to 1 aspect ratio, that would require no larger than a 3.2 mil thick dielectric. So that dielectric thickness is going to get set up inside of your layer stack manager, and then these other numbers are going to get entered into the PCB design rules and constraints editor. Now, another important set of rules that is required for BGA fan out is your solder mask rules. And I think this is something that people are very quick to gloss over, but this goes back to what I was referencing earlier with solder mask defined pads versus non-solder mask defined pads. And depending on the size of your via pad and how close those vias are together, you might be forced into using non-solder mask defined pads. Now, one of the things that drives this is the amount of copper that you need to have exposed in the footprint in order for a BGA to solder onto the PCB. That minimum amount of copper copper that you need to have exposed, or the maximum amount that you need to have exposed, is defined in the IPC 7351 standards. Now, I've shown a table from the IPC 7351 standards several times in different videos, and if you want to read an article on how that standard impacts BGA footprints, go ahead and take a look at the link in the video description. The other thing that drives that is the amount of solder mask that you need to have between those pads in order to maintain a minimum amount of solder mask webbing, or a minimum solder mask sliver. And you can see here that they are defining the minimum webbing or the minimum sliver value here in this section of the table. Now, if you're going to have non-solder mask defined pads where you basically open up and apply a positive expansion value around the edge of a copper pad, you would need to have a minimum of either 4 mil or 3 mil solder mask web width between those two pads. However, if you're going to have solder mask defined pads, then what this next line tells you is the distance over which that web needs to extend over the copper. So basically this is telling you that you need to have at least 2 mil of solder mask covering over the edge of that copper in your design. Now, this first line gets entered into the solder mask sliver value inside your design rules. This is a little more difficult because it's both a sliver value, but also it's a solder mask covering value. So it's a little bit different. And there really isn't a way to distinguish between non-solder mask defined pads and solder mask defined pads in the design rules. So this is something that you set up in your BGA footprint, and once you set it up, you're just going to have to leave it based on the vias pad size that you're going to be using to do your fan out. Now, the last piece I want to bring up is something we just skipped over, which is the impedance section. Here, there is an impedance tolerance that they list for the standard and advanced capabilities. And if you like, you can actually incorporate those impedance tolerances into the width rule inside the Rules and Constraints editor. So to do that, you can go up here to Design and Rules, and if you create a new width rule, you'll see here inside the width rule that it allows you to specify a minimum width, a preferred width, and a maximum width. Now, you can specify those values here manually if you want. You just need to calculate the impedance at each of those values and make sure that they are correct given the width values that you enter in here. Now, if you like, you can actually enforce an impedance profile inside of this Design Rules and Constraints editor that incorporates that 5% tolerance. So if I just go over here to the Layer Stack Manager, I go over to the Impedance tab. Here I can create a impedance profile if I like, and I can specify a 5% impedance. And that 5% impedance can then get incorporated into my manufacturing documentation. Once I create this for this top layer, I can then go back to the Design Rules and Constraints editor. I can then create my new width rule. I can then assign that width rule to specific nets or net classes just using this top dropdown. Now, once I select this, you see here that it fills in all the preferred width values on each of the layers where the impedance profile was defined. Now, it doesn't automatically calculate the minimum and maximum width based on deviations from that target impedance. So it doesn't like take the maximum impedance for that 5% tolerance and then calculate the maximum width, and it doesn't do the same thing for the minimum width. You'll have to calculate that yourself and then enter those values in here into the table. However, if you create a transmission line table inside your manufacturing documentation, it will import that 5% value that you defined in that impedance profile and automatically fill it into your transmission line table, and then you can hand that off to the manufacturer for controlled impedance testing. Now, the next thing I want to do is go over control of solder mask expansion on the pads in this BGA footprint. Now, in my opinion, the easiest way to do this is, of course, to just go back into the original footprint, set a solder mask expansion value that you want to use for these pads, and just stick with that. But of course, you could be in this situation where you have to use different via sizes, and the via size is actually going to define the pad size instead of the actual pad that you see here in the BGA footprint. So let's just really quickly look back here at this capabilities table. Let's see, just as an example, what pad size we can use on these laser drilled blind vias. So you can see here for a minimum laser drilled pad, they specify an 8 mil value for the advanced capability and a 10 mil value for the standard capability. So if we go back in here and we just take a look at these vias, we can actually increase the size of these vias quite a bit without impacting or violating the clearance. Now let's suppose we're going to go with their standard capability and we're going to use a 10 mil pad size, just as an example. So if I enter in that 10 mil pad size, you can see here that we have some clearance violations, and we're just going to want to make sure that we re-pour the polygons. And then let's go ahead and also update the rules so that we clear out that DRC, and then we're going to set the minimum clearance to 3, which was one of the values inside of their table. So after I define that clearance value at 3 mil, I'll just go ahead and hit OK. And you can see here, this is what the layout currently looks like. So we have these 2 pads here that are attached to vias, but are larger than the pad size for these pads that are defined in this footprint. So here you can see the pad size is set to 8.346 mil, and then here you can see these vias are set to 10 mil. So how do we update the solder mask on all of these pads? Well, you could go back into the original footprint and you could just change the solder mask expansion value in the footprint, then update the footprint in the PCB. You could of course select all of these individual pads if you want, and then you could change the solder mask value manually, or you could use a design rule. So to create that design rule, again, just go back into the Rules and Constraints editor, and we want to create a solder mask expansion rule. We're going to do a new rule, and then we can use the custom query, and then use the within room query, just like we did before. And we select our BGA room, and then we can set an expansion value that we want that's only going to apply within that room. You could also then use the query and is SMT pin, and that's going to ensure that this rule applies only to SMD pads. So here, let's go ahead and set an expansion value of, let's say, 0 mil. I'm going to go ahead and hit OK. And then when I select this value, as long as it is set to rule expansion, you're going to see here that it automatically applies that 0 mil expansion to this pad because it is within this room. Now you'll see here that the solder mask on the rest of these pads is defined as being manually set. Again, if I just set them all to rule, you'll see here that it automatically updates and applies the rule value rather than the manual expansion value. But this is something that you would normally control inside of the footprint. You can, of course, change it inside the PCB layout if you want, but a good idea would be to go back to the original footprint for this component, select all of the pads, and set them to rule expansion rather than manual expansion. And that's going to allow you to then control what is the pad mask expansion directly from the Design Rules and Constraints editor using the within room query. Thanks everyone for watching this video. I know this has been quite a long discussion of design rules for HDI PCBs, but every single one of these small features is very important for your design, especially in terms of manufacturability, because the last thing you want for your HDI design is to get it no bid from your manufacturer. If you like this video, make sure to hit the like button, hit the subscribe button, leave your comments and questions in the comment section, and last but not least, don't forget to call your HDI fabricator, folks. We'll see you next time.